Hello everyone, welcome back to my computer project. Today is another video from my computer. I am still working on my RAM boards, but that's going to take me a while. So I thought I'd introduce you to what I've been doing in terms of the instruction set, because I have to design that before I can actually build any of the hardware, because it will be built into the hardware. So I've been working on this Markdown document. By the way, this program, Remarkable, really good for working on Markdown because you can write it in here, instantly appears over here. Anyway, so this is not a completed document. It's still a work in progress. So there's certain sections that just won't be completely filled out yet, like this hardware section. So that doesn't include all the RAM stuff, the controller sequencer, the clock, all that stuff, because that should all be listed here as well. But I need to pretty much confirm that half of what I think about that is correct. You know, things like the clock, its maximum speed, and all that stuff. Anyway, so yeah, the control word. So this is basically a list of all the things that will have an input and an output. So like the registers, you can tell them to read or write, and same with the memory address register, memory in and out, all that stuff, including the program counter clock. No op, that's actually not a part of the control words. I don't know why I've put that there. That's basically an instruction rather than that. But yeah, no op would basically be the default state of all these, so all of them doing nothing. So some of these things don't actually have hardware yet, or even listed here. So like there'll be another register for flags, such as the subtraction overflow, which will enable me to do jump instructions. So you can compare, or you can put two values, then put two instructions into the register, then into the registers. Then depending on what the overflow flag is, you can choose one of those registers to use as the address. So you can jump conditionally to different addresses. I haven't actually put that all in here. So this doesn't actually even list all the instructions I've designed yet either, because I had another document that was just text, and yeah, I haven't converted that all over yet. But anyway, I'll go through some of the instructions I've got, and even at the bottom there's some example programs. So yeah, the instructions. So fetch. So this is the most basic instruction, and it's actually a part of all other instructions. It has to be done at the beginning of all instructions. So it basically increments the program counter and inputs it into the memory address register. So this will get the next part of memory. So this could be another instructions or an operand or something like that. Actually, it'll be an instruction. So I sort of do this again in some of the instructions to get the operand. So yeah, some actual instructions for doing stuff. So set A and set B, these are for setting the value of the register, or register A or register B, directly to a value. So you put in that and then you give it a value and it will set it directly to that. And yeah, these are the parts of the control word. So this as well, these are all parts of the control word that need to be set in order to get that instruction to work. And yeah, the number of instruction cycles at the moment is a maximum of 6. I think that's all I'll be needing. So yeah, those are for setting values, and these are for loading values. So this is where that maximum of 6 comes in, because this can only have 4 cycles, or this can only be done in 4 cycles. So what loading does is like setting, but instead of setting the registers to a value, it sets it to the value given at an address. So this is an address in RAM. So yeah, so you can say register A loads some value from this part of memory, and the same with B. And output just takes what's ever in the A register and outputs it to the display register. Some arithmetic functions. So we got add. Okay, so there's some interesting things here. So add, whatever value is already in register A, it takes the value at the address, puts that into B basically, and then it adds them together. So it'll be A plus whatever the value of the address is. But I have some other bits as well. So add directly takes whatever's already in A and B, the registers, and just adds them. So it doesn't do any loading or any setting or anything like that. It just takes what values are already there and adds them together. the reason this is interesting is because the ALU outputs, I mean not directly, but it outputs to the A register. So you'll see here it actually outputs to C. So ALU out, C in, then it goes to C out, A in. So the ALU outputs to register C, but then C just copies over to register A. So that's because A is meant to be the accumulator, but because my system, my hardware isn't clocked in any sort of meaningful way, it can't, the A register can't input to the ALU and also output at the same time. It would just cause noise, random number generation basically. But yeah, so that's why it outputs to C and then C swaps over to A. This is actually useful for other things as well, but I haven't, like I say, I haven't written all the instructions yet. So there would actually be a swap instruction as well. So you can take what's in A and B, swap them around. So what was in A now is now in B, and what was in B is now in A. So this is useful for Fibonacci sequence, for example. And you can do that without loading and storing from registers to memory. But I'll show you that at the bottom because I've got two examples of that. But yeah, subtract, same as add, it just sets some of the ALU settings and does a subtraction instead. You'll also see it does it do that? Oh no, it doesn't actually do it yet. I was going to say it should output the, if it has an overflow. It doesn't actually do that yet. Same with add actually, it should have an overflow, like the 9th bit basically. And yeah, like addition directly, it has subtraction directly. So whatever values are already in A and B, it will subtract them. Storage, so you can store what's in a register into memory at the given address. So yeah, that's like the opposite of load. So that's quite helpful. Flow. So this is what this is the section I was filling out last time I looked at this. So jump is basically the jump instruction. It's not conditional. So you just say jump to position, and this would be a memory address of another instruction basically. So you see it, program counter memory address in, then it goes, is this correct? Piece memory address register in. Okay, so yeah, once it's done the fetch, it does that again and puts the next address into memory address register. Then it puts the what's in memory there into the program counter. So you're basically jumping to the operand, and then it will continue the program. So you can just say jump back to 0, and it will just loop the program. I think that's correct. Program structure. This is just this is going to be a list of notes on how to write the programs, because like we have labels here. So if you have, so rather than just writing explicitly what part of memory a bit of data is in, you can put a label on it instead, and then just use that label, and it will point to whatever the value was. So this basically is a memory address of whatever value comes next, and that's explained there. So this will be a lot more extensive. And some example programs. So not all of these are useful, like addition here. This program uses 7 bytes and needs no extra memory. It simply takes 2 numbers and returns the result on the display. So yeah, so this also uses labels, which are written up here. So you can say load A x. So this is loading the value of x, which is here, which is actually 5, into register A. So register A here will contain 5. Then it does add the value at position y, which is 7. So it will add 7 to 5, and you'll get 12. Same with subtraction, does pretty much the same thing. So here's where we start getting into some actual decent programs. So this is just counting up. It doesn't do anything to initialize, so whatever the register is at the beginning, it will add to that. So yeah, you can set a label to the start of the program. You can add x to register A, which is 1. So whatever's in register A, you'll get +1. And I noticed I haven't actually put an output here. Yeah, so you, hold on, let me find that. Addition, so you, wait, I have, no I haven't, subtraction, counting up. So you would actually need to do out there as well. Otherwise you're not going to see it, are you? So that's what that does. So adds 1, puts it to the display register, jumps back to the beginning, adds 1. So you'll just see that counting up from whatever to 255, and once it hits that, it will loop back round, so you'll go 0, 1, 2, 3, 4, whatever. So that will be a good test program. These might be good test programs, but this is actually smaller. It's 1, 2, 3, 4, 5, 6 bytes. So I don't even need to finish my RAM board to start working on the control sequencer and all that stuff, and the instruction board. But yeah, I kind of want to work out what more instructions I would need before I do that. Anyway, here's the Fibonacci sequence. So this is it written in 13 bytes, and this is significant because it uses only register, load, and store. So if I didn't want to use the other instructions like set and some other things like the add directly and swap, which I haven't actually written up here, but I did mention it. But yeah, so what this does is it adds the next number in the sequence is the last two numbers added together. So usually what this does here is it tries to do that, and it uses store and load to swap in and out of memory the next or the last number. And this takes up 13 bytes, which is fine. That would actually work in my 16 bytes. Yeah, so I mentioned here, the downside to this method is that x and y will no longer be 0 and 1 after the first run. So these are ones that we've explicitly set, but once you've run the program, those are going to change. So the next time you run a sequence, you'll have to set them manually again. And would have to be manually reset. Such functionality could be implemented by going over 16 bytes. So this program here isn't very useful if I wanted to start writing programs with just my 16 bytes. So that's why I added some of the other instructions. So this is the same Fibonacci sequence, same function, but it uses only 9 bytes. And it does this by using the set A and set B functions. So I can set those to 0 and 1. Those are the starting numbers. And I can start a loop. And here I do the adds directly. So what would happen is 1 would be added to 0, which would return 1, which would set register A to 1. So then it would be 1, 1. And then the next number would be 2. So, and then, yeah, so you want the registers to be swapped, which is what we're doing here. But here, I've actually added a swap function. Because I have register C, I could just take the values of A and B and swap them. And then you just run the loop. So this is a lot smaller, and yeah, I kind of want to add these functions to be able to do this, but these like store and load are more useful functions, instructions generally. So yeah, that's what this document is for. It's just working out how much do I need, what should I start with, and stuff like that. Because I am going to try and make the instruction ROM board sort of swappable, so I can sort of put some instructions in, like just slot it in the computer in the project, and then if I decide I want to change it later, or if I expand the control or something like that, I can just swap it out or fix it or something like that. I don't want it to be like a permanently fixed thing. But yeah, that's what I've been writing, and I'm still working on it. Once it's finished, I'll upload it to GitHub, and it'll be I'll make it public so people can look at it. I'm also going to be working on a simulator, so not like a circuit simulator, like just a program simulator. So I'll have like this hardware simulated, so you'll have all these registers, and you'll be able to see the values that are in them. You'll be able to see what's on the bus, and you'll be able to see the clock and when things are on and off. So all these things will be displayed, and it will be sort of laid out like this. You'll be able to write programs in here and see them executed in the machine. So it'll be a little emulator basically. And yeah, the idea is to get these running in an emulator, so as a proof of concept of the instruction language. And I don't know when I'll be able to finish that. I did start it, but I'm probably going to start again because I started it ages ago, and then I'm not really sure what I was doing. So I'll start that again, maybe see how far I can get in a week, and maybe I'll do a video in 2 weeks. Yeah, so once I've done that, I can actually start getting a good idea of what I actually need to add into the machine itself. But yeah, thank you for watching, and I'll see you next time.